You're going to see that this is easy.
I hope so. I'm feeling good about it right now.
It can be. It really is just like, okay, what rule am I choosing first? Welcome to Study With Us, where I help Ari and you get an A in Organic Chemistry 1 this semester. Make sure to download the practice problems, try them out, and follow along with us because this is going to make so much more sense once you see how easy acids and bases can truly be. So you had a quiz.
I did.
How did that go?
Good. It went really well.
What'd you get?
10 out of 10.
Oh, okay, great.
Yeah.
Again?
Yeah.
Okay, on acids and bases especially. That's not an easy topic.
I know.
Okay, and then you watched the community video. How are you feeling right now after seeing everything?
Acids and bases, I think, just kind of scare me because they scared me in Gen Chem, I'm not gonna lie. So now I look at it and I'm like, oh no. But this actually makes sense. I think it's just like all the little rules that are thrown in, and then I'm like, wait, why is this different now? And then I look back and I'm like, oh wait, I did know that. And then I don't know, if I see examples, I'm like, oh yeah, I did know that, and I just doubted myself. So it's things like that, I think, that make me a little nervous. But
okay, we'll work on it.
Okay, that's perfect.
Let's dive into the first one. So what we're gonna do is we're gonna list the following in order of decreasing acidity. So we're going to do this two ways for each kind of example, where we're first going to start off with just using the pKa to be able to help us with that, because you will possibly be given that for, I know your professor was like heavy on like, hey, let's just look at pKa. And then we're also going to look at the actual like factors.
Okay.
So that can help us because you'll notice that sometimes pKa, you can't always depend on it.
Right, right.
Because it might not even be on the list.
Yeah, that's true. That's a good point.
So let's just start off here. What does decreasing acidity mean?
So from most acidic to least acidic.
Great. So that's what we're ranking it.
Beautiful.
So we're pretty much just trying to see which one is going to be the most out of these.
Okay.
And we'll rearrange it accordingly.
All right.
So looking at this, do you remember, without even looking at the pKa table, which I'll bring that in a second, but do we think something is already the most acidic, or like what are you thinking?
I would say because we're pretty much just looking at like the last part on all of them.
Good.
So I would start comparing electronegativity.
Good. You're already looking at
right?
what this is. It is.
Nice.
So, and that's a key point there that you saw. This is the only thing that's changing. That's exactly correct. That's what you should be looking at.
Sweet.
So, yes, so then electronegativity, okay, if we didn't know the pKas, what's the most electronegative atom?
Oxygen.
Good. What's another thing we should also be concerned about if we look at sulfur?
The size.
Yes.
Is that right? Yeah?
Yes, you're right. You're right.
Okay, good.
So good. So the two factors, if we weren't looking at pK, is electronegativity and size. So we would start off with electronegativity since that was the main difference here. And then we go back to pretty much how everything works, how electronegativity is going to be higher in this kind of corner. And then size increases as we move down. And remember, there is a key exception here. Which one is going to win, essentially, be more acidic, the sulfur or the oxygen?
The sulfur.
Yes.
Right.
Why?
Because it has bigger size.
Yes, because it's bigger. Yeah. That's really what it is. It has a larger size. So that is going to be the most acidic.
It is the most acidic. Okay.
And the reason for that is because of size.
Oh, nice.
What do you think is next?
Then I would say the oxygen.
Yes. Perfect.
Okay.
And then the reason for that is electronegativity. Now we're comparing these two.
And then I would say the nitrogen, because the nitrogen's more electronegative still than the carbon, and then it's just a carbohydrogen. So
Exactly. That's correct.
Yay.
Yep. And that's the main two reasons. So we started off with electronegativity. That's what was changing. Whenever we're comparing sulfur and oxygen, I know, okay, well, size is going to win.
Right.
So that's most acidic. Now we can also look at the pKa values specifically for that. So if I were to look at this, we're kind of pretty much seeing what is this functional group? Like what is it close to our pKa values? What would you say that functional group is?
Wouldn't that be the sulfide? Is that one?
So it's not. It would have been our thiol.
Oh, because it's a hydrogen. Okay.
Our group, yeah, or some sort of carbon chain, and then that SH.
Okay.
Yeah. So this has a pKa of 10, which remember pKa, the smaller it is.
The more acidic.
Yes, the more acidic. So we want a smaller pK
Right.
for it to be more acidic, so because it's a lower pH. And then if we had, what's this one?
That'd be a alcohol.
Yes. So our alcohol now is between 16 to 18. So, yep, that's already
That makes
more,
sense, yeah.
so that's not as acidic. We keep going down. Now I have NH2, which is a what?
Amine.
Yes. And that's a bit more basic.
Oh, I see.
So our amines are 38 to 40 range. So that's why it's at the end. What is this?
That's just an alkane.
Yes.
Okay.
You're good.
I like go through
That's an
all of them.
alkane. Good.
Okay.
And that's the worst. I'd say that is the least acidic out of everything.
Okay.
So that would have been like 50 plus. So yeah, that's why it's least acidic.
Okay, that makes sense.
So sometimes if you get a pKa table, it can be very useful because you're pretty much just looking at what's the number and arranging it accordingly, you know, in descending order in this case.
That makes sense.
So, and by descending order, I'm not talking about the actual value, right? Remember, it's kind of reversed, where if this was like 10 and this was 50, that wouldn't necessarily be decreasing order.
Right.
It's decreasing acidity.
Okay.
So a low pKa is most acidic, a high pKa is least acidic.
Okay, that makes sense.
Cool. Good start. Next one. So same thing, still in decreasing acidity. So most to least acidic. Just looking at this, what do you think the most acidic possibly is?
The carboxylic acid.
Why?
I just know that that one's always going to be really acidic, but I mean, it has the electronegative oxygen, and then it has like, yeah, it's pretty much actually the only reason I can think of the electronegativity.
Okay. Now, what's changing each time?
The center, like the central atom on these ones. And
Right.
then I guess this one has more like branching off of it. Does that make sense?
So we don't look at necessarily branching
Okay.
for these. When one thing that we saw that totally right, you saw, okay, the centers are changing. This is a carbon, sulfur, and sulfur. So these have sulfur.
Right.
When I see sulfur, what's the main thing I should be like, ooh, what am I pointing out?
Size?
Size. Okay, so these have the size on their side, which makes it more acidic.
Oh, I see. Okay.
So right there, boom, that's out.
Oh, just kidding then. I was wrong.
But it's good to know.
But then,
you know?
I mean, that's helpful. Yeah.
Yeah.
That makes sense.
So immediately when we're comparing, when we see, okay, really we're comparing that carbon versus the sulfur, well, sulfur is larger and it's more electronegative.
That is true. Okay.
So now I'm kind of looking here and I'm like, okay, well, there's pretty much a similar thing.
Yeah,
the
there's
only
pretty similar.
difference, what's the only difference?
Right here, that.
Yes, this has an additional oxygen, which makes this more,
Electronegative?
yep,
Oh.
makes it more electronegative. Plus, so this has now size, electronegativity. Not only that, what do we know double bonds are?
They're alkenes.
Sorry, like when I mean double
Oh.
bonds, learned about this. Resonance can occur in the double bonds, the lone pairs.
Oh, I see what you're talking about. There's more
Yes.
resonance, there's more acidity. Is that what you're saying?
Exactly.
Okay.
So it goes back to resonance. When we have more resonance, structures or resonance in general, that stability of the conjugate base is better, which makes it more acidic.
Yes, okay.
So this also has resonance.
So it's got all of it.
It's got all of it.
going on. Okay.
So because of that, that makes it the most acidic
Okay.
for those reasons. So I'm going to scooch this guy over. And now we're pretty much comparing these two. But I know that this is better because of size.
Yeah.
Not only that, this has another electronegative atom compared to this one.
That's true. That's true. Okay.
So there we have it. It's pretty much, okay, I know this is actually going to be the least acidic for these reasons.
Oh, okay.
So that was just looking at our factors, which again, remember, ranking factors. We go from charge, we look at electronegativity, size, resonance, inductive effect, really how close our electronegative atoms are to each other and how many they are.
Okay.
That's really what inductive effect is essentially saying. The closer electronegative atoms are to each other, the more acidic they're going to be.
Okay.
And then hybridization.
Right.
Let's also look at the pKa values just to compare if you wanted to do it this way, that works, just knowing these rules. And if you're also given pKa values, that's another great way to just kind of solidify, like, yes, this is the answer.
That's true. Okay, I see what you're saying.
So in this case, this actually wasn't given to you on your pKa values. I did add it. So that's why I'm like, you're not always given them.
Yeah.
So you can't always depend on the pKa values. This is like a backup.
Okay, that makes sense.
So I know that this looks like sulfonic acid.
Right.
And it's fine that it doesn't have the R group. It's really just whatever is closest to it.
Okay.
So I know that this has a pKa of -9, which is very low. And I know a low pKa means it's going
More
to be
acidic.
more acidic, exactly. And then this one, this isn't even on here. So that's why, again, I can't compare anything. I don't have that value. So this is where I had to know that resonance is the reason why this won.
Oh, okay. I see what you're saying.
And electronegativity, having another oxygen. And then lastly, looking at that carboxylic acid, that's a 4 to 5. So drastic change.
Right, that's true. That is true.
Yeah. So that's how we use this.
Okay, that's helpful.
Next one. So we're still doing the same thing. How would you think to go about this one?
I would start looking at charges.
Good. Good. Okay, cool. So charge is going to be our first factor that we're looking at.
Yay.
And I'd say let's just kind of group the ones together that are charged and the other ones that are neutral.
These guys.
What's our tiebreaker here?
Because then you just go down, right? So you just look at electronegativity.
Good.
Okay, which would make oxygen more electronegative.
Perfect.
So that would be automatically our most
Yep.
acidic. Okay.
That's how we're using this. So great.
Nice.
That helped me basically eliminate these two. Now I know the next deciding factor is either going to be electronegativity, resonance, one of those.
Right.
So great. That's done. I know this is the next one because it's the other one that has the positive charge.
Right.
Another thing is knowing that if we have a positive charge, that makes it more acidic. But if we were asked a different question, if it was, let's say, like, how basic is it? If it's positively charged, it's not basic.
Least, yeah.
Yeah, it's the least basic.
Okay. That makes sense.
What do you think we're looking at here?
I feel like my answer every time is just going to be electronegativity.
That's fine. This one's
Okay,
correct.
I'm
That
like,
is
and this
correct.
is in the order, right? It's supposed to be in?
Yes.
Okay.
So perfect. The deciding factor here as well is electronegativity. Oxygen is more electronegative. And again, the main thing we're just looking at is the end portion of this because that's the only thing that's changing.
Yeah, okay.
So not too bad.
That's not too bad.
I'm also still going to compare pKa values, again, just to double check my work. I know that this is a what on this list?
Oh, that is a alcohol.
Good. And it's protonated. So protonated just means it has an additional hydrogen. So a proton is just H+.
Okay.
So it has an additional hydrogen and it does have a plus charge.
Okay.
So that would look like this. I know that that's roughly like -2. So okay, -2, yep, that's low. What about this one?
That is an amine.
It is an amine, however, this one specifically is protonated, like it has a positive charge. So those are very different in like pKa values. If we see the amine, this one's neutral.
Yeah.
So I can't classify this as that.
Oh.
I have to see that, oh wait, this is charged. The closest thing is going to be that ammonium ion just because it does have that positive charge.
Okay.
So, and then that's also worlds apart because that could lead us wrong.
Yeah, that's a big jump too.
Yes.
Okay.
So that's why another thing, okay, great. This helped guide me to the correct answer. Yep. In case I accidentally classified it wrong.
Yeah, that does make total sense. Okay.
So great, that would have been roughly 9. And again, these are rough estimates. It changes whatever R group we have.
Oh,
So you
okay.
can't necessarily
Can't
give
always
like,
be 100%.
yes, yeah, it can't be
Okay.
exact.
Like ballpark. Okay.
What's this guy?
That is also an alcohol.
Good. So that's an alcohol. I know that's roughly 16. And then keep going down. Now what's this?
That's an amine.
That's an amine. Good. So that would have been 38.
Okay.
That makes sense why it's at the end.
Okay. That's how it makes sense.
Okay.
Yeah, that clicks.
Great. You're going to see that this is easy.
I hope
is.
so.
It
I'm
can
feeling good
be.
about it right now.
It can be. It really is just like, okay, what rule am I choosing first? I'm going to go from charge. Okay, what's next? Electronegativity. You're kind of just spot the difference.
Yeah.
See what rule you can kind of like justify to win it over. If there's a tie, pick another thing. What does this one have other than this one?
Yeah.
What's the advantage that this one has over this
that
one?
That's
Yeah.
true. That's true. Okay, I like that. That's helpful.
This next one, ACS exam question, I'm pretty much always throwing them, right? So this one specifically says, of the following species, which one is the weakest acid? What is this saying?
Basically, which one's most basic?
Exactly.
Right? Okay.
Yes.
I'm like,
Which one is the
that's pretty much
strongest
what it
base?
says. Okay.
Yep. That's really what it's asking. I know that everything is now reversed. You know, if something had resonance, it's not going to make it a weak acid. It's going to, we actually want something that doesn't have resonance. Yeah. So I would just pinpoint each one and say, which one is the strongest? Not that one. Not that one.
Cancel.
And then get to the
Yeah,
end.
okay, I agree. So first of all, I went to look at charge, and they all have charges, so they don't really do anything for me. But if we look at electronegativity, I know that 3 of them have oxygen, except that one's ether, right?
It is.
Here?
Good. That is a protonated ether.
Okay.
What's this one?
That's a protonated oxygen. I mean, that's a protonated alcohol.
Good.
Okay, that's what I was trying to
Good.
say.
So yes, and this is where our pKa values can be helpful if that's given.
Okay. If they're given.
If they're given. And then I'll show you how to, if it's not, how to actually use this.
Okay.
So, okay, great. I already know this we said was a protonated alcohol, all right, -2. Protonated ether, well, this is in the same group.
Oh.
So I can't say that one is necessarily better than the other from this information.
Right.
So because of that, these are actually out.
That makes sense. Also, they're really acidic.
They're really
That's, like,
acidic,
really okay.
exactly. So I know, okay, that won't be the weakest.
Uh-huh.
So now that I've canceled those out, I'm looking at these two. And then I could see, what is this?
Protonated amine. Is that right? Or no,
So
the ion, the
ammonium ion.
That's
Yes,
what it was.
yes,
Okay,
yes. So
that was
it
different.
is an ammonium ion. So that's like a 9.
Okay.
9 to 10. And then this one is kind of where you're like, I don't really know what that is.
Yeah, that's different.
But what group is this? That carbon double bonded to our oxygen. Do you remember what that was again, that name?
The carbon double bonded oxygen ketone, but it has a hydrogen on it, so then it'd be aldehyde?
You're looking at the amide.
Amide.
Right.
Okay.
So in this case, it's not going to be this specific amide because it's not protonated. So this one specifically is a little bit different. This is a protonated carbonyl group.
Yes.
Just because it's kind of like, this is like think of it like an umbrella for other stuff.
Oh.
You know, so it's helpful to just know, okay, this is going to be relatively acidic because it has that protonated carbonyl group.
Okay.
And I'm just looking I'm just looking at this portion. So that's one thing. Okay, I can see pKa values. That's also pretty high. That's actually even higher than the other ones we saw. So what's the lowest one? Have to be
This one.
B. Yes.
Okay.
So there's that. Yes, I know that this is correct. But I also want to show you how to use these. So going back to what would be the strongest so that we can find the weakest.
Right.
Which one would you say, for these reasons, would have been the strongest?
I would have said the strongest. I know I just saw the pKa, so I know, but I just forgot. So I know it's between these two. If I didn't know the pKa, like I didn't just see it, my reasoning would have been honestly this one.
Hold on, going back to this one. This one would have actually been the best, the strongest, because that had a -7. That was the protonated carbonyl.
Oh, that's right.
And then these two were the protonated alcohol and ether.
That's what it was, that's right.
But how I want you to kind of look at it is we could even just go one by one and say, what is the advantage for these? Like kind of like listing, what does this have that the other ones don't? Good.
Oh,
this one has resonance.
As soon as you said that, I was like, oh, wait.
That one has resonance. What else does this have?
Is it inductive effect?
It is.
Okay.
Perfect. Inductive effect because we have multiple electronegative atoms and they're close to each other.
Oh, okay.
So it's kind of like a concept of like, hey, we have two similar ones that are electronegative. It's like a supportive group. You know, we want to be close to each other. We're kind of like and like. You know, we want to have that be stable.
Okay.
Another thing that I kind of just said, we have electronegative atoms.
Right. So there you go.
This one wants to collect them all.
Okay, that makes sense.
So it makes it a very strong acid. And then, okay, so I know that would have been the strongest. So for this specific question, that rules it out. Then when I look at these two, this one is difficult to decide.
Yeah, that's weird.
And because it's a multiple choice question, I can't really decide. You know, there's not enough information. Even looking at the pKa values, it was roughly the same. So the only thing that these really had was electronegativity that we would look at. But again, if I had to rank these, this one would have been the strongest. I would have placed these saying that they're relative, like they're basically equal. I would have put them in the same group.
Okay.
And then this one would have been the weakest because it's the least electronegative.
That makes sense.
Yeah. So that's another way to kind of like classify it if you weren't given the pKa values or if you accidentally misclassified this. You know, that can happen. So that's why I want this to be like the main kind of way that you check.
Okay, that's helpful. I like it.
Difficulty 2. For this one, we are going to give the products for the following acid-base reaction, and we're going to indicate whether our reactants or products are favored at equilibrium. So we're basically picking what the arrows would be. And then I also want us to draw the curved arrows how everything is moving.
Okay.
Before we even touch a pen right now, I kind of just want to play with this idea of how electrons are moving. And actually, let's just look at this for right now.
Perfect, okay.
Let me grab that hydrogen
Oh, yeah.
and the negative charge. And because this told us this is an acid-base reaction, the first thing I want us to do is just identify which one is the acid, which one is the base. Good?
Yeah.
Why?
Well, this is a carboxylic acid right here.
Yep, it said it in the name.
And this is a negative charge.
Perfect.
Okay.
And this goes back to basically what an acid is, specifically the Bronsted-Lowry acid. We know that this is going to donate a proton, so it has to have a proton.
That's true.
So if it's going to proton again, H+, right? Hydrogen. So it has to have a hydrogen to give.
Yeah.
This one, I know it's a base because it doesn't have a hydrogen to give. It wants to accept a proton.
That's true.
So that's why, yes, bases tend to be negative. Acids either have a proton or are positively charged. Great. Now, how is this going to basically grab the hydrogen? If that question makes sense. I can clarify what I mean. So I know that there's lone pairs there. Let me draw them in. There's lone pairs here, here, and here. We know that because this is at the end. This would be bonded to just the carbon, one single bond.
That's true.
So there are 3 lone pairs with that negative charge.
Okay, I see what
Bonding
you're saying.
patterns, right? So now when I'm looking at this, what's essentially happening is since this oxygen wants to gain a proton, it's going to reach out, and how I would draw it is pointing this towards the electrons that are going to move. That is basically going to create a bond with that hydrogen. So again, this is kind of like I'm going to grab that hydrogen. Now what's going to happen is this is going to form a bond with that hydrogen. This is no longer negatively charged. Where's the negative now?
On this.
Yes. Exactly. Because this lost a proton, so it lost a positive charge, it now becomes negative. Yes. That's really it. We just formed the products. Now, I also want to say, since this is no longer our acid and base, what did we just form? Which one is
I see what
which?
you're saying.
Yeah.
Okay, so this would be our conjugate base and this would be our conjugate acid.
Perfect. I know because this is now negatively charged. It lost a proton. This gained the proton. That had to be the acid. We always have the opposites.
Yes, exactly.
Okay. That being said, back to the drawing board.
So, okay, and this is the exact same one we just had.
Exact same one.
So you're saying. So we draw the arrow from where it's getting it from.
Yes.
See, that was really weird for me. I don't know why that threw me off.
But we want to show those electrons. So always making sure that there's a lone pair there. That's what we're showing.
Like right here? Like that? Or like more towards like the
More towards it. So I would say that this guy here needs to be pointing.
I see
So
what
it has to be pointing. That's what's
Right
going
to
to...
it.
Yes. It's not the negative charge. It's the lone pairs.
Okay.
Those are the electrons that are moving.
Oh, okay. That makes sense. Okay. And do I have to draw all of them in or just that one?
Really just that one. It's really dependent on your professor if they want you to draw them all in.
Oh, really? Okay.
But I would say that I would have been fine with you just showing those lone pairs and moving
Doing
that.
it? Okay. That makes sense.
Now let's draw the products.
Okay, so we have this hydrogen that's been donated, so... And
Good.
then plus CH.
Perfect.
No charge.
That's it. And then just going back, again, I knew this was the acid, our base. We formed our conjugate base, this guy, and our conjugate acid, this guy. So that's how it's always going to be. There's always the opposite pairing.
Yes.
Acid, conjugate base. Another way is they look the same, right? They have to look the same.
Yeah, they do. That's true.
And then our base and our conjugate acid, again, they look the same. Only difference, we're gaining and losing a proton.
Yes. Okay, that helps.
Okay, we drew the products. We showed that curved arrows, not too bad.
Yeah.
Almost done. We now have to decide which side is favored at equilibrium. What do we remember equilibrium favors?
Always the weaker side.
Good. Good. Yes.
Except that's the thing. I know that, but then I'm like, how do I remember which one's the weaker side?
So the weaker acid, really.
Oh, okay.
So this goes back to everything that we were talking about. And then again, now comparing what we just saw, which one was the acid, which one was the conjugate acid?
The conjugate acid was this one.
Yes. Those two, that's what we're comparing now. Now we just have to decide which one's weaker.
This one's weaker.
Why?
Because this one, well, first of all, this acid right here is donating a proton.
What's the advantage? What's the advantage
we're
from this
using
one?
this thing?
Yeah.
This one's more electronegative.
Yep.
Is that actually it? Is it just this one?
There's more stuff. So
I guess resonance because it has a
good.
carbonyl group.
It has a double bond.
Okay,
Yep.
okay. And then That's it, pretty much, isn't it? Or I guess inductive effect also.
Inductive effect could also be a thing because there are two oxygens close to each other. There's more electronegative atoms. This has a lot, right?
That's
so
true.
this one is stronger. It's not the weaker one. So I know that this is the weaker one. So what side is it going to favor?
The right, or I guess the product side.
The product side, exactly. Okay? It's not the reactants, which would look like this. We know it's the product side.
Yes.
Has to look like that.
The longer arrow.
Yes.
Okay.
Going to the right. Yes. Perfect.
Okay, that's not too bad.
That wasn't bad. It really isn't. Once you know, okay, how is everything going to move? And then that's another thing. I always know that the base is pretty much going to be kicking it off.
Yeah, that's true.
Okay. It has to grab a proton because this has it's not going to go the opposite way. And we're soon going to talk about electrophiles and nucleophiles after this. And that's going to be the real organic chemistry.
Oh, no.
But it's based off of these principles.
Okay.
So if we understand these curved arrows, it's going to make life a lot easier.
That makes sense. Okay, so always from what is...
What's going to grab the proton?
Okay, what's grabbing it?
Yeah,
Okay.
so this kicks it off. The base kicks it off.
Okay.
And this is donating the acid.
So could I say that it's always, like the tail of it is always at the base, or is that not really good?
No, that is fine
Sure,
to
okay.
think about it that way. It is at the base. It goes towards the acid.
Okay.
Yes. I want us to be able to see this a bit better since it's going to look more like the real organic chemistry. So first things first, who is the acid, who is the base?
This is our acid, this
Good.
is our base.
Good.
I like it.
Good. Why is this the acid?
Well, it has a hydrogen, so it's going to donate that.
Yep.
And that's negative charge. That's like my favorite trick.
That's
when they have
totally
a charge,
fine.
I'm like,
Yeah.
oh my goodness. Okay.
Yeah, that makes it easier. It's
It does,
exactly
it
why.
does.
The acid has to donate a proton, has a proton. This one has to gain a proton, it doesn't have a proton.
Right, right.
So great. Now the next thing is how are electrons going to move?
From what's grabbing it.
Yes.
So it'd be this guy.
Good.
Okay, I
we
was
have
like,
a lone pair.
to point out. So
Good.
from this, grabbing the hydrogen.
Good. So let me scooch these over. So yes, this is now grabbing that proton. And then we're now with these lone pairs, this is going to form, if I can grab it, a bond between that hydrogen. We no longer have a negative charge. These electrons, and actually, while this is happening, you know what, let me show that one more time, just because we're actually going to see multiple arrows here.
Okay.
We're going to have multiple arrows because what's happening to these electrons? They're not just going to disappear. You know, so when I take this hydrogen and form that bond, so like, okay, I accounted for these two electrons, they formed a bond between the oxygen and hydrogen. Now, that's no longer there, we don't have that negative charge. So we accounted for that. Next, these electrons go back onto the sulfur
Oh, I see what you're saying.
to then make it negatively charged.
That's so weird. Okay, that's true. That makes sense.
Because again, they can't just disappear.
Yeah.
So now that's negatively charged. We gained that. We now have formed our conjugate base and acid. So go ahead and pick which one's which.
This is our conjugate base now. It's
Good.
our conjugate acid.
Exactly. That's what we're drawing.
Okay.
So we're going to draw now.
Okay, let's do it. So. Oh, wait. Yeah, that's right.
From the lone pair, good, to the hydrogen. That's our first step. And then we said this guy is then going to move on to, yes,
Oh, okay.
because we're still showing how electrons are moving.
So on the other one,
We could have done it as well, except it didn't have that bond in between and it wasn't asking for that.
oh, I see what you're saying.
But I can go back afterwards and
No,
show
you're
you
good. So what's the difference in the question?
that this one actually had the skeletal formula.
Oh.
Versus the other one just had the
I
condensed.
see what you're
Yeah.
saying. Okay, that's good to know. And then just draw it. So.
But I do want you to get used to this.
That's helpful.
This is what it's really going to be
Yeah.
from here on out.
Okay.
Yeah.
Okay. So this will be negative now.
Good.
Like that.
Perfect. So again, I'm going to have us decide or just place everything again. Where what was our acid, what was our base, what was our conjugate base, conjugate acid, all that.
Our conjugate base and our conjugate acid.
Cool. Which way is the equilibrium going to favor?
So I'll come from my acids.
Yep.
Let's see.
We're just comparing the acids.
It will be
We're picking the weaker side.
this one.
Why?
Because if I'm comparing the sulfur and the oxygen,
Good. Which one are we looking at?
we're looking at these two. Well, oxygen is more electronegative, but sulfur is bigger, so it's more acidic. That's it, right?
That's it.
Okay.
We're comparing size.
Okay.
So
Size.
whenever we're looking at sulfur and oxygen, we're comparing size.
Okay.
Good. I like that your mind went exactly there. So then, yes, it's weaker again. Go ahead and do the flip. You got to do it on camera. You got it.
Oh,
You got
yeah.
it.
You're
Come on.
right. I know it's part of the experience. Let's see. Product side's favored.
Good.
Because it's weaker.
Yes.
Okay.
Perfect. That's it.
Oh, that's good. Okay.
That's honestly all it is. I know that it looks scary because you're like, oh my gosh, equilibrium. I don't remember what that is.
I don't know why that scares me. I'm like, oh no.
It's a big word. I don't know what that is.
How do you
know?
spell it? Just kidding. Yeah, it's true.
How many eyes are there?
know.
How many L's? Yes. So it's one of those things where it gets scary because you're also now drawing curved arrows.
Yeah.
You don't want to be wrong with that. But yes, if we're always doing that, just showing that there's lone pairs. This is moving. I'm now creating a bond between these two.
Okay.
I also am pretty much breaking this bond, and I'm now moving those electrons onto here. And you'll notice this is where they are. They're back on there, as we saw before.
That makes sense.
That's all that was.
That's not too bad.
Okay.
Okay.
Let's increase the difficulty.
Okay, I knew this was
Level 3.
I can feel it.
Yep, you can feel it. You can see it.
I can feel it. I see it.
So we're just ranking each hydrogen in order of increasing acidity. So
Okay.
what does that mean?
From least acidic to most acidic.
Yes.
Okay.
And I'm going to just give you these.
Oh, that's nice. Okay. So I would say the least acidic is going to be C.
Why? Just talk it out.